Good morning, everyone. So today we're going to present chapter 2, which is basically basics of consumer theory. Okay, so the heart of the classical microeconomic theory basically is a rational consumer. So we're going to learn how to model decision making under assumptions of rationality. Of course, along the way, what we'll try to understand is basically what we mean by being rational. Rational decision making theory that we're going to study is limited to a very particular environment, and then we're going to be expanding on this environment as we go through the class. But today we're going to do things very simple. We're going to start with what is called the classical consumer environment, which has to do with budget sets and commodities. So first we describe formally the goods and services that a consumer may consume. Okay, so we call the object of consumption commodity. This commodity basically space is the Euclidean space of size L. At this stage, we're allowing negative values of commodities, which means that you owe this amount, and positive values is that you have them. Later, we're going to specialize it to only positive values. Capital L denotes the number of goods, so we're going to study cases where at least we have one physical good. Capital L is going to be fixed in the particular applications we study. And then we refer by the subscript lowercase l any commodity. So in particular, you can think of going to a supermarket and a commodity is pretty much buying something like bread or flour or sugar, right? And the quantity of that you consume of such commodity is given by the amount x sub L. Okay. Now, the consumption bundle or commodity bundle is the vector of belongs to the Euclidean space of size L, which is this vector of entries x1 to x capital L, which quantities of the different amounts of goods. So all the vectors we consider here are column vectors. So, and this is a transpose symbol. So because the commodity space may be too generic right now for some modeling purposes, for instance, we may have to rule out extremely large quantities of commodities, or large quantities pretty much are impossible to get, or for instance, you don't allow to negative quantities, then we can actually restrict the commodity space to some subset of RL, okay? So remember that the consumption set is an abstract concept and we can just pretty much be defined according to each modeling situation. But for now, we're gonna let it be, for instance, the positive Euclidean space. So we allow zero quantities, but we don't allow negative quantities. In particular, we can change this, and very little of our theory is gonna change. In real life, the consumer cannot consume anything he likes from the consumption set X, right? So a consumer usually is constrained by his available wealth or income or any other reason. Here we're going to focus on a particular type of constraint, which is a budget constraint. So we're going to introduce this new notation. So W is the amount of income you have, amount of physical income you have. And then prices are a vector in the Euclidean space of which must disallow in zero price and also negative prices. And the consumer is then limited to choose from this budget set. The budget set is a subset of the choice set, okay? And we're gonna denote it by capital V. And this has two parameters, P and W, prices and income. And this is defined by the set of all commodity bundles in the commodity space such that the multiplication, this is the inner product with the transpose, right? This is a vector of size 1 times L and multiplied by a vector of L times 1. So this is a scalar, and this is less than equal than W, the income. Okay, so this is a typical budget line. Now, given the budget set, and then when this calls with equality, this is called basically the budget line. Now, after understanding the consumer environment, we're going to introduce what is called the demand function. This is the object of interest or the primitive of our theory. So in particular, I'm going to assume that the theorist is going to have access or observe a demand function. A demand function pretty much is a mapping that goes from the space of prices and income to the commodity space. So it assigns commodity bundles to budget sets. Okay, so you give me the budget set as described completely by the price and an income level, and then I give you the commodity bundle. This is what the demand function does. Okay, and so in particular, it has to be that the demand value evaluated at a particular price and W belongs to the budget set. Okay, so it has to be feasible. That means that prices multiplied by the physical amount of goods demanded according to this demand function at prices and income level W are less than equal than W. Okay, so the demand function, as you know, this is actually a multi-value map because this is actually the value is a vector. So when I write down x sub L of PW, this denotes the quantity of commodity L consumed at prices P and wealth W. So observe that X, of course, for now is going to be assumed that it's an empirical object. Okay, so that is a lot to assume because we haven't explained how this came to be, right? What does it mean to observe a demand function? So it means that I have to be able to know what the consumer is going to be demanding for any price and income level, any. So how many prices and income levels there is? Well, there is an infinity number of them. So can you run an experiment to do this? Well, not really, because you will have to run an infinite number of experiments for each prices and income level, right? For instance, you will have to do it for, imagine two goods. You have to do it for the vector 1, 1, vector 1.1, and vector 1.2. And in fact, explore all possible prices, right? So in reality, right, this doesn't happen. So our theory is going to be done now under this very strong assumption. But as we go through the class, we're going to learn how to simplify and to understand our theory when we only have finite demand data. That means only a finite number of experiments where I observe consumers choosing for a budget set a finite number of times. But right now we're going to study this ideal case where you have access to the full demand function, okay? And, you know, in more practical sense, this demand function can also be estimated econometrically, right? So you're going to be assuming somehow that you have access to a perfect estimator of demand function. Okay, so having introduced our object of interest, which is a demand function, and now we're going to start understanding what is consistency in consumption, okay? So before proceeding, I'm going to just write down a simple example of a demand function. So you have a clear idea what I mean by that. So a typical example of a demand function is a Cobb-Douglas demand function. So in this particular case, I'm gonna define the demand function as follows. Remember, this is a vector, right? So because this is a vector, I have to write down, in fact, in a transpose way, the information that I need. This is just for two goods. And the first demand is going to tell you that you will consume 1 minus alpha, alpha being a share of the budget. And you're going to consume 1 minus alpha of that particular income for the other goods. So this is a demand function, right? It's a system of functions because you have actually two values here. The first entry is telling you the consumption of good 1. And this is alpha for alpha between 0 and 1. This is a Cobb-Douglas share. And this is the fraction of income this consumer is going to allocate to good 1. And then, of course, how much of that good can this consumer buy? Well, the amount that the price 1 allows him. And for good 2, you have to do 1 minus alpha W divided by P2. Okay, so this is an example of a demand function. Of course, you can have way more complex demand functions, and this is just one example, but this is what we're dealing with. Okay, and I know this description for all prices and income. Now, consistency in consumption. So now that we have established the ingredients, so to speak, the environment and the primitive of the study. So what is the environment? Is the commodity bundle space, and we have prices that are positive, income that is positive, and we have a demand function. So now we're going to proceed to the modeling part of our study. So initially we'll assume that I'm not gonna go actually to a utility maximization part. So I'm gonna approach this problem of consumption modeling from a different perspective. And this is called pretty much consumer consistency. And the first approach to do it basically is gonna be about trying to impose some restrictions on demand that will basically allow us to do demand prediction, but without really being specific about how the utility process is behind it. So in a way, you have to think about this part as trying to do consumer theory without a utility function. And instead of a utility function, we're going to use what is called a consistency in consumption. So the idea is that if you have an intelligent consumer has to follow a set of rules. And these rules will make this consumer predictable, right? So we're gonna pretty much state certain rules of consumption that will be called in the end axioms of consumption. And these axioms of consumption that are rules that all consumers follow in a way, that would be the hope, will allow us to predict consumption behavior, right? So we will impose a set of restrictions or axioms, as I say, rules over Marshallian demand function. Marshallian demand function is the name we're giving to this demand function that we're studying, right? That we expect to hold in all situations, irrespective of details. Okay, so rules of behavior have to hold in all situations, irrespective of details, okay? Here we understand modeling consumption basically as restricting the set of allowable behaviors. So how can you make scientific prediction? Well, you have to find patterns, right? So what we're doing now is trying to establish some patterns a priori, and then understanding what are the implications for that for demand behavior, right? So you may not want to call this modeling, right? Because we're not gonna do modeling in the strict sense. In the sense, we're not gonna write down, for instance, a maximization of a utility function of certain type. But in any case, economists like to think of these axioms, right? As minimal requirements, and as the minimal requirements that a demand function has, right? Sadly, we must underline that these restrictions are pretty much the product of introspection. So how these restrictions or rules came to be? Well, basically they came through the mind of theories. So economists, as well as other social scientists, are also the object of a study, right? So we study humans, we study decision makers, and we are decision makers ourselves. So a lot of the inspiration for early theories of behavior came from introspection. So that means basically that a lot of these rules, are pretty much things that theorists imagine how people should behave. So science is about how people do behave, right? In reality, not how they should behave. But historically, because of introspection, lack of experiments, theories pretty much found that it was instructive to think about a normative way about thinking how humans should behave, almost in the trying to think about the ideal way of deciding. And in fact, we're going to see that this approach is fruitful in some way, even if it's not empirically motivated, because it's going to give us a set of tools and a way of thinking about the problem of decision making that's going to be useful. And in fact, I think it's actually transportable, and it can actually be used even when we are motivated by experiments. So what I'm telling you is that this very classical theory you're going to learn, has some limitations because it's not empirically backed, but it's still useful in the sense that we're going to be able to follow the same kind of template when we extend this theory to now empirically backed extensions, right? So the first restriction we're going to impose in our demand function is called the Walras law. So Walras law is basically telling you the following. It says a demand function X is said to satisfy Walras law even only if this inner product multiplication of prices times the demanded quantity is equal to income, exactly equal to income. So what it means is that a consumer will exhaust all his resources in order to demand whatever quantity he's demanding. So nothing is left on the pocket, okay? So no savings, nothing is left on the pocket. So this first Walras law pretty much is almost a normalization. So from all the restrictions we're going to study today, this is the one that is harmless in a way because it's really hard to actually test. So most data that we have access to is going to be pretty much people purchasing something in, say, Walmart or Costco. So in most cases, we observers, economists, cannot see how money the consumer is willing to spend at Costco, right? That quantity is not even well defined. So imagine even in a complete cash-only world, you wouldn't be able to observe how much cash in their pockets consumers have. But even now, it's worse, right? You have access to credit. Really, this budget is really mental. So the consumer is going to mentally allocate an amount of money they are willing to spend at Costco, and they may hit that target, right? So in a way, this Walras law is telling you that, whatever they spend, I'm going to assume is the income, right? So this is a working assumption, and I'm happy with it. So you may find little objection, but as I told you, this little simple restriction rules out a lot of consumption behaviors that we don't want to pay attention when we think about the consumer problem. So this is a very first natural restriction that simplifies our life. The second restriction has a little bit more psychological content, behavioral content, and this is called the no money illusion, or more mathematically, homogeneity of degree zero. So the demand function is said to satisfy the homogeneity of degree zero property if and only if for any alpha greater than zero, if I take prices and income and I multiply it by this scale alpha. So imagine alpha is equal to 2, for example. So I double prices and I double income. What will happen with demand? Well, demand should remain the same. Why? Because even if your prices double, your income also double. So in real terms, you are as well as before. So you can afford as much as before. So this is about this rule, this restriction is trying to eliminate nominal illusion. So a consumer that will fail this will be subject to nominal illusion changes. So for instance, a consumer that whose income is increased by double, and then the prices also increase, but the consumer, for instance, is not rational, is not consistent, fails to understand that prices double because of lack of attention. So maybe they don't notice right away that prices have increased. In that case, their demand will change, right? So that will be a failure of money illusion. We're not going to study that case. This is more modern beyond this simple theory we're going to present today. So for today's theory, we're going to rule out this complex behavior of lack of attention. And we're saying, look, consumers can think in real terms. And in fact, if I change and scale prices and income by some scale alpha, demand quantities should remain unchanged, okay? And so now we're going to introduce the third constraint, which is way more restrictive and way more important than the previous two. And this is called the weak axiom of revealed preference, or WARP. So as I go through the class, I'm going to refer basically as the WARP or weak axiom exchangeably. And I'm going to say the axiom now, or the rule now. A demand function X is said to satisfy the WARP if and only if for any two distinct price well pairs, that means an initial price pair PW and another one P star W star, such that the demand function at these two price and income levels is different from each other, it follows that first, if the amount consumed according to the demand function to the second price income level, P star W star, is affordable at the original price and income level, then it has to be that the quantity demanded at the original PW level is not affordable, is strictly more expensive at the price star and given the income level star. So right now, this sounds like, you know, a tongue twister. Seems complex, but it's not complex. And I'm gonna explain it in a bit. We're gonna introduce now a notion that's called reveal preferences, and this will make very simple to understand the weak axiom, okay? So the weak axiom, what it's telling you in words is basically the following. It's telling you that there is some stability in choices that consumers make, okay? The reveal preference name comes from the idea that by observing demand behavior, the underlying consumer preferences can be revealed to the observer, okay? So now let's define such a notion. So a reveal preference relation, R super D, stands for directly reveal preferred to. And this is a binary relation on a consumption space set defined as follows. So take any two pairs of prices and P1, X1. X1 is a consumption bundle that I pick according to P1. To what income? Applying Walras law to the income P1 times X1. So income is not written here because it's already implied, okay? Income is P1 times X1. So my data here is a price and a consumption bundle. And then I have another price and another consumption bundle, P2, X2. So all of these are vectors, right? Now, I declare the binary relation X1 is directly reveal preferred to X2 whenever the multiplication of the original price times the original bundle is greater than equal than the original price multiplied by the second bundle. So in words, this is telling you super simple information. At prices 1, this consumer chooses X1. But at the same price 1, X2 is actually cheaper. So what happens if the consumer picks X1 when X2 is cheaper? It must be because X1 is better for the consumer, right? So this is an inference. So now I'm declaring this object, which is an empirical observation, as X1 is directly reveal preferred to X2, okay? So now this is a data point. I have declared that X1 is reveal preferred to X2. What is the rule? So Warp is telling me now, remember what I wrote before, if I rewrite this in terms of this reveal preference relation, right, I'm gonna be able to say the following. So remember what I said originally. By the Warp hypothesis, I have that the demand in the second price income level, star, is affordable at the original price level income situation. So that means that because of Walras law, it has to imply that the original income demand function, which I call Z now, as you can see, XPW, is directly reveal preferred to Y. What is Y? Is the second demand situation. Now, if that's the case, then Warp requires you, the consumer, to not flip choices. So that means you cannot strictly change your preferences. So it has to be that we do not allow that now Y is strictly reveal preferred to Z, okay? So in particular, it means that we're not allowing that this inequality happens, which equivalently means that in terms of our original language, that P star multiplied by XPW is strictly not affordable at the income star level. So in simple words, the premise of the Warp is telling me a key piece of information, that at the original demand function is peak when the second demand quantity is affordable. So that must mean that the original quantity, which is called here Z, is strictly and directly reveal preferred to the second quantity Y. So Warp requires the consumer to not change in the new budget situation their preferences. So they cannot flip and suddenly now prefer Y over Z. So you do not allow that Y is better than Z in the strict sense. So it has to be in terms of budgets that the original demand level is no longer affordable. So you don't pick it because you cannot purchase anymore. at P star, W star, XPW is no longer affordable. Okay? So this, of course, condition was established originally by Samuelson, and he said, look, this condition is so natural that I will call it a weak axiom or revealed preference, because so weak and robust that it must be true, right? Now, we know better currently, right? And this is, of course, a behavioral hypothesis. It may or not be true in data. And as we progress in the class, I'm going to tell you empirical evidence and experimental evidence against this axiom, at least in its simple form. So we're going to be thinking about why people will fail this as we progress. But now we're going to start from this very simple model where we just assume this is true. So remember, this is the third axiom of a set of axioms that now we're restricting to this particular model, okay? And in particular, and we're almost done with this particular video, I'm gonna conclude with the implications of these three axioms in terms of demand behavior. So what I'm gonna do is say, look, as we progress, I'm gonna introduce the notion of comparative statics. So this is the behavior of demand elasticities, roughly. So how derivatives of demand change. And we're gonna introduce an object called the Zlotowski matrix, which is an important object that captures a lot of information about the derivatives of the demand function. And using this information, which is about how demand changes with price changes and income changes, we're gonna study the implications of the three rules that we introduced before, in particular the weak axiom or revealed preference, on the behavior of these elasticities through the Zlotowski matrix, right? Okay, so we need to introduce this Zlotowski matrix object and the derivatives. So first of all, I'm gonna introduce some preliminaries. And the first thing is the matrix of price effects and demand of a demand function. So this is a matrix of derivatives, which is basically the collection. So an entry LK is basically the derivative of the demand function entry L. So this is the derivative of the demand of good L with respect to the changes, differential changes in price K. Imagine a situation of two goods. So you have bread and butter. So this will be, for instance, the entry 1, 2 will be a good 1 bread with respect to changes of price of good 2 butter, right? And the diagonal will be the own price change. So will be 1, 1 will be bread with respect to price changes of bread, and 2, 2 will be butter with respect to price changes of butter. And the off-diagonal elements, 1, 2, and 2, 1, are the cross derivatives, okay? So this is the substitution matrix, price effects, okay? Now we're gonna introduce the vector of well effects, okay? Well effects is just a vector, column vector of size L, where any entry is the differential change on demand of good L with respect to income. Income is a scalar, so that's why this is just a column vector. So it's not a matrix as the previous object. So the previous object is of course size L times L. The key object of this particular section is the Zlotowski matrix. So Zlotowski matrix is basically an object that takes the substitution matrix and adds to it a correction term. And this correction term is the income effects multiplied by the quantity demanded at this particular price income level. So why do we need this object? So remember that if you were living in a calculus world, like what you saw before, so you take a function and you want to understand how much it changes with respect to a change in a parameter, the parameter of the function. What do? You take a derivative, okay? That's great. Now the issue here is that we are not studying just a function alone. We're studying a function, demand function, that lives with a constraint of the budget constraint. So as prices and income changes, of course, we're gonna get changes in demand, but these changes in demand are restricted by the affordability, which is described by the budget line. Now, this restriction means that I have to take into account these changes in the budget in some way when studying the differential changes or the comparative statics of demand. So this second term is going to correct the the differential behavior of substitution behavior of demand with respect to price changes because of the changes due to affordability. So as you change prices, you're going to be changing how much you can afford given the income level data. So this is a correction term. I'm going to explain this more in a second. But right now I want to understand what is the Zlotsky matrix. So take the Zlotsky matrix and study the entry L sub k. So in particular, imagine, for instance, the entry 1, 2. So 1 corresponds to the good, 2 corresponds to the price. So now the first entry is just the changes in demand of good L with respect to price K. So good 1 with respect to price 2 in my example. And then I take a correction term, which is nothing else than the changes in good K now with respect to income level. And then this multiplied by the amount purchases at level L, of good L. So think of the Zlotsky compensated demand function. So I'm going to introduce now this object, which is a new object that I call the Zlotsky compensated demand. So this object is different because I take a demand function, the original one I studied before, and I have prices, and I have now a commodity bundle Q. Now say I want to make, this Q is a commodity bundle that I want to make affordable. So in particular, whenever I change prices, you will always be able to purchase commodity bundle Q, okay? That's why you're compensating this consumer, because this consumer is always sure that he can purchase Q. Now, if I derive this compensated demand function with respect to prices, I can use the chain rule, and I get here that this is, of course, matrix derivatives. So it's not as trivial, but you can do it entry by entry, and you will get a conclusion. Is that the matrix of derivatives of this compensated Zlotsky demand is equal to the substitution matrix. This is the first argument part. And then because of the chain rule, this is the second argument derivative. So it's income effects multiplied by the chain rule, multiplied by Q transpose. So in particular, let's say I want to ensure the consumer to be able to afford the original commodity bundle. So Q is equal to X, X being the original commodity bundle. If I replace this in the previous expression, then I get the Zlotsky matrix. So that means that the SPW is equal to the substitution effects plus the income effects multiplied by X. So that in particular, this means what I'm saying is basically that the Zlotsky matrix is correcting for changes in income. So what is ensuring is that I'm studying the substitution effects of prices while I'm making sure that the consumer remains compensated. That means that I'm giving you enough income such that the original consumption bundle is still affordable, okay? So this is a very important operation because now it actually makes sense to compare price changes because now I'm already correcting for the implied purchasing power changes. Okay, and so I'm gonna end this video with pretty much the implications of the Walras law for the Zlotsky matrix. The first thing is very simple, so I'm gonna go very quickly over this, and this is just taking the Walras law and then just stating the Walras law, and I'm gonna derive this Walras law, and I'm gonna get two implications, okay? These two implications basically come in the form of a multiplication of prices times income effect is equal to 1, a multiplication of prices times substitution matrix is equal to minus demand. So this is just simple derivatives and calculus. So there is nothing really economical about this, but this gives us some information about the behavior that's ruled out just by the Walras law. And in particular, the first implication is telling me that there has to be at least one good in the set of L goods that has to be a normal good. What is a normal good? From your undergraduate classes, you have to remember that a normal good is a good which income derivative is positive. So normal goods means that as income increases, your demand increases of that good. An inferior good, which is the opposite of a normal good, will have this derivative with the opposed sign, will be negative. So the fact that 1 written in scalar terms is that the multiplication of the income effects times prices is equal to 1 means that at least some of these derivatives has to be positive, right? So the Walras law is telling me that at least one of the goods has to be normal good, okay? So in particular, let's say you have only one good. So that means that it must be the case that that good is normal. So imagine you want to model, for instance, given goods. Given goods are inferior goods, okay? So how many goods do you need? You need at least 2 goods to be able to have this. Okay, so now implications of the homogeneity of degree 0. So this particular one is very simple. It just tells me that this Zlotowski matrix, if I multiply it by prices, is equal to 0. So what it means for the people that remember linear algebra is that the rank of the Zlotowski matrix is not full rank. So the rank or the number of columns that are linearly independent is less than the dimension of the Zlotowski matrix. So what is the dimension of the Zlotowski matrix? L times L. So the rank must be less than that, okay? And in particular, I know that a point of singularity is actually prices. So as you can imagine, this object here, right? This looks like an eigenvector eigenvalue. So that means that the 0, right, is an eigenvalue of S associated with eigenvector price. You can do the proof yourselves. It's very simple and nice to do it. You can have to derive only the homogeneity of degree 0. You derive with respect to the parameter lambda, and then you obtain this rule. Finally, and I'm going to end with the most important implication. This is the implication of the weak axiom of revealed preference. So remember, the weak axiom of revealed preference is the key axiom that tells you that consumers do not flip preferences. So what is the implication in terms of the Zlotowski matrix? Well, it turns out that this implication is a more general version of the law of demand. And this is called the compensated law of demand. So we say that X satisfies the compensated law of demand if and only if you have 2 prices and I subtract the second from the first, and then I have the inner product of the difference between demand functions at the first price level and the second price level, then this difference is negative. So what it means is if prices increase, then quantities must decrease. So they have opposite signs. But there is a caveat, and that's why it's called compensated law of demand. And is that these 2 price well income situations are not any price income well situations, are a particular one, such that the new income situation is equal to the new price, P star, multiplied by the original bundle. So what it means is that at the new price and income situation star, the original commodity bundle is still affordable. So only when that happens, when that Zlotowski compensation is done, then this inequality holds. So the law of demand here only holds for compensated pairs of prices and income. So now how does this relate to the Zlotowski matrix? Well, we're gonna actually see that the compensated law of demand in its differential form is just an implication on the Zlotowski matrix, okay? So first we're gonna show quickly that Warp and the Walras law imply the compensated law of demand. In particular, this is very simple, so I'm gonna just go quickly over it. But in particular, we let Z be equal to the original demand, Y be the second demand. By assumption of Walras law, we have that P star X star PW is equal to W. This is not by Walras law, sorry, this is the compensation, it's Zlotowski compensation. And then by Walras law, I have that P times Z is equal to W. And also I have by Walras law again, that P star times Z is equal to W star. And this is by the original assumption, and we also have the Walras law again. And then we multiply P star times W minus Z is equal to 0. By Warp, we know that this must be that the original bundle at the new situations is less than or equal than W star. And it must imply that P times W is strictly more expensive than W. So it has to be, if combining this information together, that P times Y, P times Z is greater than or equal than 0, or P times Y minus Z is greater than 0. We subtract this from P star times Y minus Z, which was equal to 0, to obtain the inequality of the compensated law of demand. P star minus P times Y minus Z is strictly less than 0, okay? So this is the compensated law of demand. Now, let's conclude this video by studying what happens with, I study the Zlotowski matrix and the compensated law of demand. So I start with the compensated law of demand, and then I consider a case for which the price change is infinitesimally small. So let dP be the very tiny vector, so pretty much negligible of the difference between P star and P. So that means that this equation here can be written simply as the difference in prices, dP, times the differential of demand, dx. So what is the differential of demand? Well, this is a total differential, again for calculus. So dx is equal to the substitution matrix, dp xpw times dp. This is the argument, the first argument. Now, plus the second argument, dw xpw times dw. So by Slotski compensation, I know that the changes in income has to be such that the changes in prices can still afford the original bundle, okay? So that means that pretty much dp times xpw is equal to dw. I just transposing an scalar, so this is equivalent. And then finally, dp dx is equal to what? dp parentheses the total differential of dx. So I just replace this here and I obtain this expression. I multiply the dp inside, and then you will recognize that this object here is the Slotski matrix. So now I'm telling you that dp dx is equal to dp spw dp, and this is less than equal than 0. Okay, so what does it mean? So this, you know, you need again the notion of negative semi-definiteness of a matrix. So a matrix is negative semi-definite whenever you multiply this matrix by a vector before and after, as here, dp times the matrix times dp. Remember, dp is any change in any direction. So this is pretty much an arbitrary vector. The only thing we're doing is we're shrinking it to make it super small. And we're saying that for all such vectors, this matrix here will give you this negative value, okay? So this is a generalized notion of negativity for matrices, right? So matrix is not negative as an scalar because it has way more entries, right? So for instance, it can have some negative entries, some positive entries. So how do you know if it's negative semi-definite? Well, the only test is to test for all possible vectors, all possible directions, whether this multiplication dp times spw times dp is less than equal than 0. So we're saying here that the Slotski matrix is actually negative semi-definite, okay? So please go and check also online any clarification about negative semi-definiteness. This will also you learn with Maria. So I leave it to you. So thanks. This is all for today. Bye.